In this video, we are going to cover general linear models and those models using least squares estimation. That's where we have like the sum of squares, where it's x minus mean of x squared. Add up all the x's across a particular group and divide by n. So in a later video, we'll talk about mixed models, another technique that uses something called maximum likelihood estimation. And there's a lot of reasons for choosing that one. Mostly the main one is that it gives you, for repeated measures, different ways of looking at the correlations between the items, and it also allows for missing data. Now, missing data in the least squares analysis is only important when we start talking about repeated measures. So today we're going to start off with correlation, the Pearson binary correlation, and we're going to look at that for a bit, and then move to linear regression, one-way analysis of variance, analysis of covariance, and then repeated measures analysis of variance. So this is a brief introduction and just a little reference for you to go to if you need a little help with these different things. The main feature, common feature among these models is that the outcome variable, the dependent variable, is continuous. Now when we talk about correlation, we're going to show that both variables generally are continuous variables, or at least interval or higher in the number scale. All right, for our starting motivating example, we're going to use the Stone blue light study. In that study, she had three groups. One was a control that, well, first of all, the objective of this study was to determine if blue light affected sleep, and that if it did, could you cut down its effects with various techniques. So the control group had no correction, or they had plano spectacles. The other second group had blue blocking glasses. These were glasses that chromophores were embedded in the glass, and they actually did block blue light. And third was a software solution like on your computer or cell phone when you go into the night mode. And so people kept a diary of how much blue light they were exposed to at night in terms of computer, television, and so forth, and then wore a Fitbit to determine the total minutes they were asleep, they were awake after they'd gone to bed, the number of times they came awake, rapid eye movement time, light sleep time, and deep sleep time. There is some question as to whether or not the Fitbit can. The Fitbit apparently is pretty good at determining the minutes of sleep that you have. Maybe a little weaker in the rapid eye movement and deep sleep area. Okay, so let's look at correlation now. All these things we're going to be talking about, all these analyses, are within the Analyze part of your menu. And we're going to go down to Correlate, Bivariate. We can see in this one there's the Pearson, which is it's the parametric correlation that has various assumptions around the normal distribution. There's Kendall's, Tau, and Spearman, which are non-parametric and are based on rank orders. The Spearman, basically, you rank your data and then rank the data in all the groups across all the data, even across groups. You rank it 1 through n, and then you just run a regular Pearson correlation. the Pearson correlation, of course, so ranks, there's 1, 2, 3, 4, 5. It's an even number all the way down to the bottom. Whereas in the Pearson, values take on whatever their values are. There's no intervals. There can be duplicates. You know, it's a different way. Kendall's tau is something different. We don't really use that one too much. Okay, so let's look at our correlations. So we're just going to go across treatment groups for this. We're going to look at cell phone usage, computer minutes, TV, the blue light. Actually, maybe we'll start with blue light because that's basically a sum of these items of cell phone, computer, TV, and then there's books, which of course there's no blue light in books. You just, unless there's maybe blue light reflecting off the white page. Then there's the time the spectacles were worn, the amount of time, the amount of time between dinner and going to sleep, minutes of asleep, minutes of awake, number of times awake, rapid eye movement, light sleep, deep sleep. Those are all continuous variables, and we're going to correlate them with each other. We're just going to do a giant correlation matrix. Now, for tests of significance, we're going to do a two-tailed test, and we are going to flag significant correlations with an asterisk. You'll see that. And also, we're going to show the diagonal. That's a check. We do that because it provides a reference. Okay, let's see what we have. All right. Now, this is a correlation where we have blue light through deep sleep, this way and that way. Blue light to blue light has a correlation of 1. It's the same thing. We get number of people down here under N, and those differ. It does the correlation based on the data that's available. For example, here there's only 97, whereas here there's 99. Excuse me. Put my glasses on, and it's 67 versus 69. Okay, you can see that this correlation right here between cell phone and blue light is significant, and there's a double asterisk, and it's significant at p less than 0.001. So each cell looks at the two variables, gives the correlation, its significance, and its n. Now correlations can go from -1 through 0 to +1, and the null hypothesis is that the correlation is equal to 0. And so the test, when it's significant, is just that it's different from nothing. That's a pretty low bar, actually. And our guidelines, generally speaking, are a correlation is, we want to keep a correlation greater than 0.3 or R squared at 10%. Now those are a little off, but that's approximately it. Now, when you're correlating something like a puffer test versus a Goldman test for IOP, you want those correlations to be pretty high, up in the 90s. But for most other things, we're going to just, in general, use that 0.3, but it really kind of depends on what you're looking at. So this is a correlation. You can see we have our diagonal. The bottom half here is a mirror image of the top half, so every correlation is done twice. Here's 5.575, 0.575. This is called a Pearson correlation matrix. Spearman would be very similar. All right. Now the next thing we want to do is a linear regression. We're going to come down here. There was correlate. We're going to go right under that is regression. And it has a bunch of choices. We're going to focus for now on the linear regression. In later talks, we'll talk about binary, multinomial, and ordinal regressions. Maybe some curve estimates, but probably not too much of that. So here's the linear. And what do we have? Well, in this case, we're going to just look at awake. No, we're not. We're going to look at asleep. And for this one, we're not going to look at blue light. Rather, we're going to look and see whether cell phone, computer minutes, or TV, as recorded by diary at night, and we'll add book too, which of these has an influence on the amount of time you're asleep. So there's some other things here. Selection variable, you could select by certain things, but generally we don't do it. That you give the case some labels, have a variable that would help you identify cases later if we had picked some statistics that needed that. And you can also give it a weighted least squares weight for the different things based on various characteristics. We're not going to be concerned with this in this talk. So some of the statistics that we want to look at. Well, we want to get the estimates of the regression coefficients. We want to know how well the model fits. We could do R-squared change if we were going to do a stepwise, but we're going to put all our variables in at once rather than one at a time. The descriptives aren't that useful in this context without splitting them into groups. The big one that we want to do is Clinicality Diagnosis. This is multiclinearity. This is when the independent variables are correlated with each other. Because if they are, they steal variance from each other and can mislead you on the results. So that's an important one to look at. All right. And under the options, we could exclude cases listwise or exclude cases pairwise. Now, in the multiple correlation, you saw that we had missing data where some were 67 and others were 69. There, the option was to include cases pairwise. If any of those three dependent variables or the independent variables or the dependent variables is missing, we're going to get rid of the whole subject. So we'll see how many subjects we end up with. We start with 69. We'll see what happens. All right, let's continue. There's also a technique called bootstrapping, which is a way of simulating the answer. And if you have a misbehaving distribution of values, the bootstrap can help you to get an answer. It's kind of the unequal variance, non-normal distributed kind of question technique that gives you an answer. We might do that in a later video. Okay, so let's see what we have. So this tells us the variables that we put in. We entered them all at once. This is our model summary. And so using those three variables, we came with a correlation. This is a multiple correlation now of 0.472 and R squared of 22. So these four variables have accounted for 22% of the variance in the sleep minutes of the dependent variable. So they're sharing the variance with the dependent 22%. Adjusted R square is an R square. You notice it's smaller than 22. It's smaller because it takes into account the number of independent variables you have. At an independent variable, the only way the r squared can go is up, because you keep counting, you account for more error instead of actual underlying variance. And so this formula takes into account the sample size and the number of variables that you're looking at. The ANOVA, we have a regression model. That's our 4 variables predicting a sleep. Those variables, when you consider the predictors, come up with a certain amount. And so of variance, or sums of squares. And then the residual is once you fit this model, then you have a predicted score for each subject, and then the difference between prediction and not is called the residual. When you divide the sums of squares by the degrees of freedom, you get the mean square. And this mean square divided by the residual, that gives us an f-test. Now the sums of squares, when they're divided by the total, that gives you the r squared. So the square root of the sums of squared divided by the total, that square root is r. You can see we rejected the null hypothesis that all the coefficients, or that the correlation was 0. Now let's look at our coefficients. So this is a model. We have what's called unstandardized coefficients, their value, and their standard error. Now the first coefficient is really a constant. That's the y equals a plus bx, the a and y equals a plus bx. And then these values are the b's. And so we have 4 of those. And if we were going to predict, if we knew how much time how many minutes a person spent at night on their cell phone, their computer, their TV, and reading a book, if we plug that into this formula here, we would get the predicted amount of minutes. That would be our model. And so we have our y equals a plus bx, so it's 421 plus minus 6.162 times the the cell phone minutes, plus minus 9.559 for the computer, and minus 0.439 for the TV, and minus 8.196. So what this is telling us is that the more time you spend on these, an extra hour or an extra minute, no, this is an extra hour of cell phone, reduces your sleep by 8 minutes. I was kind of surprised that this was a negative, because it's not a blue light based subject. So you would think if you spend a lot of time on the books, you should have a decreased effect of the blue light. But I think this might be just, in fact, if you're keeping your brain engaged, maybe, I don't know, it's speculation, keeping your brain engaged at night for too late just before you go to sleep, that also impairs the amount of sleep you have. Now, in this particular case, since the time is all in the same unit of measurement, the betas are pretty, these coefficients in terms of importance of the various variables will parallel the betas and the t's. So what that means is that -9 is the highest value. That means that the computer was the one instrument that did the most damage to sleep. And the coefficients is the standardized coefficient. It's almost like it gives you an effect size. This is essentially a standard deviation of variability, and it's 0.42. It's not super high in this case, but that's just what it is. The t-test is the beta divided by the standard error, and that's testing the null hypothesis that the coefficient equals 0. And if it's significant, as it really only is in the computer, then it's rejecting the null hypothesis and saying that it's unlikely you would get a t-score of 3.4 if the null hypothesis were true. So we say that computer was significant. Now, over here we have tolerance and variance inflation factor. These two are related. 1 divided by 0.816 equals 1.226. So it gives you both of these, but they're essentially identical, just one's the reciprocal of the other. And these tell how much these different values are correlated with each other. And in this case, generally speaking, the rule of thumb is if you're less than 5, it's not a serious problem. And so it does not look, in fact, like these guys are correlated with each other very much. So some people, if you use a lot of cell phone, you're not likely to use a lot of computer. And in fact, since it's a little hard to, I'm surprised that there wasn't more of this, because if you are spending all your time on your cell phone, you're not at your computer. I suspect if we did a frequency distribution of how many minutes and hours were on each of these, that the computer would dominate, and there wouldn't be that many hours of cell phone or TV or a use. Maybe some books, though. All right, so this is the multiclinearity. There's no real correction we need to do in this particular case. All right, next, let's go to a model that is basically an analysis, a one-way analysis of variance. Essentially the same thing. It is the same thing as a regression, but it adds these variables that, or it adds treatment. We can add treatment, but treatment, we have treatment 1, 2, and 3. You wouldn't put treatment in here, because then the coefficient would say, well, 2 is greater than 1 and 3 is greater than 2, and it doesn't have that ordinal nature to it. They're categorical. So if we were going to add that in here, what we could do is we could go to transform, create dummy variables, and let's create a dummy variables for treatment effects. Let's give it a name, just call it group, and say OK. And then what we have done, if we go back to our data, we look over here on the right and stop. Sorry, wrong database I called up. So this is the database that we used, and here are our 3 variables. So if we come over here, we see we have Control Bluebacher software, and it's created a 0, 1, variable for group 1, a 0, 1 variable for group 2, and a 0, 1 variable for group 3, or the software blue blockers control. Now let's run our regression again. And let's add in those 3 variables. Then we run it. And then let's see what we get. Now this time look at our coefficients. And you can see that we have variables for treatment group blue blocker and treatment block software, but there's no control. And doesn't really tell you what it's doing, but what it's doing is when this value, when you're doing your formula to add up everything, if the group was a blue blocker, it would give it a 1, and then you would add this coefficient times 1, which would be the coefficient, to your formula. So you'd add 6 minutes. So the blue blockers give you an extra 6 minutes. The software, if it was a 1, would add 3 minutes. Now, in this case, it's a 1 or a 0. In this case, it's a 1 or a 0. And if it was the software group, you wouldn't add in the 6, you'd only add in the 3. If it was 0 in both, you wouldn't add any. So these coefficients are relative to the control at 0, which gets no additional contribution. So this is 6 minutes relative to control. This is 3 minutes. 3 minutes relative control in amount of sleep time. And here you can see we still don't have any variance inflation factors. But here also, we don't get significance. So it's just a problem. But anyway, so this is a one-way analysis of variance. But there's a better way of doing, a more convenient way of doing analysis of variance. And that's we analyze, and we're going to do general linear models, because this is a general linear model. The regression was a general linear model. We're going to do univariate, and we're going to do a sleep, and we're going to do treatment group. Now, we don't need to do the dummy variables, because analysis of variance, those statistical packages that do analysis of variance, they say, okay, in your fixed factors, you're saying that you have basically categorical data. If you had continuous data, then you would come down and you would put it here in the covariate. We'll see that in a minute with analysis of covariance. We're going to stick blue light, total blue light down there. So here we're just going to do treatment group. Now, we could actually, we could make this like our regression equation, and we could put in our cell phone minutes and our computer and our TV minutes. And now we have a regression equation. If we go to our, well, we can calculate our means for the treatment group. And that's after adjusting for everything. We can see what our treatment group means are. And these have been, just like in regression, where when you look at TV minutes, it's after you've controlled for cell phone, computer, and book. In this case, when we look at treatment, it's after we've controlled for cell phone, computer, TV, and book. And so we're going to then compare the main effects using this least squares, but we could do a Bonferroni if we wanted to, Bonferroni. But we're just going to keep it at least squares. Okay. And then for this particular time, what we're going to do is we're going to look at our parameter estimates. And then we could do, well, we want to do homogeneity of variance tests. And that's pretty much it for this set of for this particular example. So again, we can do that bootstrap if things were misbehaving. All right, okay. Now what do we get? Now treatment group comes out as a single variable, but if we look at these guys, oh, I forgot book. Let's do it. Analyze general linear univariate book. All right, if we look at the significance, we see that it matches the levels in our regression. In our need to get rid of this one. Notice how you can go to the outline, highlight stuff, and clean up your output. So here's our coefficients. Notice we have, for significance, for cell phone it's 524, computer it's 001. Down here, our parameter it's 524 for cell phone and 001. It's the exact same thing. It's just that it makes it easier. Oh, and notice that it creates, in this case, it creates the two dummy variables, but for control, it gives it a 1 or a 0. Blue blockers, it gives a 1 or a 0. The treatment group of software adjustment, it gives a 0. So everything is relative to the software, rather than in the regression equation when we created our dummy variables, it was relative to the control. So if you have 3 variables, you only need 2 dummy variables because it's 1, 0, 0, 1, or 0, 0. Those are how the 3 groups are defined. And the ones that are 1, 0 or 0, 1 are relative to the one that is 0. That's what those coefficients are relative to. So the control group has 3 minutes less than software, and the blue blockers have 2 minutes less. But here we can look at our basic tests of between subjects. We have our groups down here. We have our sums of squares. Our F is the mean square for treatment divided by the mean square error. And so it's not really too impressively significant there, for sure. So this is the probability of rejecting the null hypothesis given this particular F statistic of 0.14, and you can see that probability isn't very high, so we do not reject the null hypothesis. In fact, the only time we reject the null hypothesis is when we look at minutes of computer. And so minutes of computer is significantly, or hours at the computer at night, is significantly related to amount of sleep. And when we come down here to the parameter estimations, we see that the computer is minus. So you lose 9 minutes of sleep for every hour increase in the computer. and that's a significant effect. Now some of the other things that it gives us with our treatment group, now the parameter estimates are all the information you get with respect to the continuous variables. And but for the discrete variables, the categorical, the treatment group, you get estimates. And these estimates are the mean number of minutes of sleep for each of these groups. We can see there's not very many minutes separating them. 6 minutes for control versus blue blockers. 3 minutes versus control for software. But, oh, and then down here, we get pairwise comparisons. So it looks at control versus blue blocker, control versus software, blue blocker versus control, blue blocker versus software. Now there's 3 comparisons, but you get 6 because it does all combinations in all directions. All right, now let's say we want to, we should have up here Levine's test. Yes, here's Levine's test. And notice we were able to go ahead and go with that because our test of equality of error variance was not rejected. So the null hypothesis is that the variances are equal, given that we got this F value was not sufficiently bad enough to say we should reject it. So we assume, or we fail to reject. All right. Now, our post-hoc tests that we did here were just the least significant difference comparisons. We did not do any adjustments. We could have done some adjustments, and actually let's go through and do that as an example. So analyze general linear model, univariate, and then let's go to our post-hocs were grayed out because we added all of this other to make it a regression. So let's get rid of those. And now we can do some post-hoc tests because the only thing we have is a one-way analysis of variance. This wasn't really an analysis of variance one way before because we had those continuous variables in the covariate section. So now we're going to come in here, we're going to do our treatment group. And then we've done LSD. We can do Tukey. We can do Bonferroni and continue. Now we didn't find anything before, so we're not going to find anything here either. But just to see what it looks like, here are multiple comparisons. It does just like it did with the LSDs, compares all the pairs twice, and it gives the significance. You can see the Tukey, the p's are closer when we come up to the, oh, I deleted it. So this significant, I think, was like 0.4. And now it's 0.8 with a Tukey because you've adjusted for the multiple comparisons, so the p-value gets bigger. And in all cases, it's not significant. But notice the Bonferroni actually has a lot of ones. It's so conservative, none of those values were significant. And 1's as high as you can get. You can't go above 1 for significance. Okay. Next, let's look at creating 84% confidence intervals. Now, there's no way to plot this in SPSS, so we have to go outside of SPSS into Excel. So we're going to copy this the estimates because it has the means. I'm going to go into Excel and start a new spreadsheet. I'm going to paste. Now, you get a choice of two pastes. One which carries the format over, but actually kind of, I don't know, I find it sometimes harder to work with when you're trying to move stuff around because it merges cells and stuff. This gives everybody their own cell. And now let's say we want to, well, the other thing we need to do is figure out what's our denominator. Now, we get here this standard error. We get upper and lower confidence intervals. We come here, I think we should maybe give that a few more decimal points. Oh, it doesn't have any more. That's interesting. Be exactly 9. Okay. Let's go back to our output. And let's copy in the between subjects. The test of between subjects effect. So we copy, and we go into Excel. I hope that's the wrong one. Excel, and we paste. Now, here is our mean square error term. And we would like to get the root mean square error term, which means we're going to take equals the square root of this value. And this is the pooled standard deviation. And then if we come back to our output, scroll up to the top, we notice that one of the pieces of information that it gives us is the n. It also here it does a number of ways of looking at the equality of variance. When it's taking the value and subtracting it from the mean, it can subtract it from the mean, the median, or some adjusted value, just a whole bunch of things. We mostly just look at the first one. We see 0.808 is not a significant difference, so we have no reason to believe that we don't have equality of variance. And then in this table, it tells us what our sample size is, which is 23 in each group. All right, so let us go back to Excel. And so what we want to do is we want to create a bar chart. So we're going to go and highlight these groups. So we have the name and we have the means. And we're going to insert a chart. And here we go. Now one of the things I like to do with this is make those bars maybe just a tad wider. So the gap width I'm going to decrease. And that's too much. And then I'm going to put in error bars, and I'm going to want to see both the top and the bottom. So I'm going to get my picture out of the way here. I'm going to fill them with blue, but I'm going to make them more transparent. So I'm going to move this guy over here. Now I'm going to be able to see my error bars. Now what about these error bars? We know that in a confidence interval, we're going to do 84% confidence intervals. So to do that, we need to have a t-value that's going to give us that 84% width, so that's equals t inverse 0.16 because it's a two-tailed test, and when you put in 0.16 it's two-tailed, but it's actually going to give us the direction in one way. So half of 16 is 8, so that's the amount that we want on each tail. But to get to that, we put in the 16. And the degrees of freedom are the n, which is 23, minus 1. And we're calculating the error bar for each mean. And so we just do the sample size of each mean. And then if these error bars overlap, we're going to say they're significant. And if they don't, then we reject the null hypothesis. If they overlap, we accept the null, or we don't reject it. And if they don't overlap, we reject. So that's the t-value. Now we have to multiply the t times the square root of n, of t times the standard error. And the standard error equals the standard deviation divided by the square root of n, in this case 23. And so we get 9, come down. Oops. All right, so I copied that down and I got zeros. Why did I do that? Well, if we look here and we click up here, we can see this was the value that went into that. It's the standard deviation, that's the g, divided by the square root of n. Now, I just copied those down, and when we come down here and we click up here, we notice that it makes a relative move, and that's not good. Now, what we could do is come here and click up here, come over to this cell here, which is G16, and we can put a $sign in front of the G and a $sign in front of the 16, and the $sign anchors that to be this particular value. It's the column G at the row 16. The other thing we can do is hit the function key F4. I don't know how you do that on a Mac, but on a PC you just hit the function key and it puts a $sign in front of both of those. Now when we copy it down, it fills it all in. So on this one, we can see it sticks this G16 here. All right, now we want to create error bars. And we want to use these widths to make little bars over here. Now how do we do that? We come up here, we first click on the bars, and then we have a chart design up at the top. Chart design and format. So we click on chart design. We come over here to add a chart element. And the chart element that we want to add are error bars. Now, unfortunately, these basically, I don't know how they work, but what we want to do is go to more error bar options, and they come over here, and we select custom and specify the values, and then it's highlighting this, so we want the positive error bars, so they're going to go mean plus 9. And then we're going to click on this little bar down here, and we're going to do the same thing to give us the mean minus it. And that's what our error bars look like. And while that looked like it was going to be a big difference, in fact, because the error bars are so wide, it didn't have an effect. Of course, it's not that they were so wide, it's that our scale was so small. If we come over here and click there and go to our format, our axis, and we make the minimum 0, then we get a graph that looks like that. And that looks like the nothing that it is. So those are error bars and how to create our 84% error bars. When there's a difference, when they're not overlapping, you have a bunch of groups up here. You don't have to do little bar things with asterisks crossing them to figure out which ones are different. You just look to see which ones aren't overlapping. And those are significant at an unadjusted, that is, not adjusting for multiple comparisons, unadjusted p less than 0.05. All right. Oops. Nope. Now, one thing that we could do is the next thing we want to talk about is analysis of covariance. Now, we sort of saw that in the last example when we were doing all the individual things. And that, in fact, could be considered an analysis of covariance, because you're looking to see if there's a difference between groups after adjusting for cell phone, computer, TV, and book use. And it can have multiple, you can have multiple covariates. In this case, we're going to just have one. But before we do that, analysis of variance has an assumption. And that assumption is that the relationship between the covariate and its groups that is constant. The slope. So well, this will be easier to show in a graph. So let's go to our legacy. Go to a scatter plot. Simple scatter plot. And the y is going to be asleep. Minutes of sleep. The x is going to be our covariate, which this time we're going to just use total blue light. That's the sum of computer, TV, and cell phone, but does not include book. And we're going to set our markers by treatment group. So we're going to get a, well, we'll get different dot. Well, let's just look and see what we get. So we have these different colored dots. We have control, blue blocker, and software. Now, we want to look and see if the lines between these different groups are parallel. And the way we do that in SPSS here is we double click on this. Now, generally speaking, SPSS is a terrible program for making nice graphs. But it's pretty nice for making quick and dirty graphs. And that's what we want here. We just want to check our hypothesis, our assumption that the slopes are equal. And to do that, we come over here and we look, and there's little dots in here and multiple lines. You look closely. This is multiple dots, and it adds a fit line to the total. This adds a fit line for each of the subgroups. So it looks like that. And these lines are crossing over. So if you don't have much blue light, then or let's see, wait, which one is it? What's red? Red is the software. The software is flatter across the whole range. The green is the blue blocker, and the blue line, colorblind here. This line, whatever color that is, matches with the blue blocker, and the control is here. Now, in general, you can say that the more blue light you have, the less sleep you get. So the more exposure, the less sleep. And these lines are crossing. If we were to do a test with the interaction, we can test this with it. In this case, when you're doing your analysis, you do an interaction. You add an interaction term. So let's go ahead and do that. Analyze general linear model univariate. And here we have to come up to the model. And we're going to build our terms. And we want treatment group in there. And then we also want I don't know why it doesn't have. Let's go back. Let's continue. The covariate isn't there. Let's put in blue light. Go to our model. And let's have treatment group and blue light. So we have, as our model has treatment group and blue light by treatment. So you don't automatically get this. You have to work at it if your lines aren't parallel to get that. Now you can, again, it's going to just give you the means for the treatment group, and this is a problem because it's just the main effect. It doesn't really help you with the interaction. So let's look at this. And in fact, in this case, we have oh, I forgot something here. In our model, we also have blue light as a term. So we have a main effect, and we have two main effects, and we have the interaction term. And when we look at that, we see that blue light is significant. The treatment by blue light is not significant, but that's because there's really not much difference between those lights. But let's say, this is just for an example, so what we'll do is we'll say, okay, let's assume this is significant, that they weren't parallel. What would we do in that case? We would come up to transform, and one of the things we could do is recode into a different variable, and we can make blue light the blue dose. And what we're going to do is do a median split. The median values are the median blue light value is 3.25. So if values are less than 3.25, we're going to give it a 0. And if they're greater, we're going to give them a 1. So now we have values. We have a new variable in our setup. And it's called blue dose. So it has ones and zeros. So now we've made the continuous variable a categorical variable. And now we can run a two-way analysis of variance, where we go analyze general linear univariate. Instead of a covariate, we're going to add this blue dose variable and make it a two-way test. And we're going to see how that works. For the expected means, we're going to add, wait a minute, cancel. Let's go to our model, full model, instead of our customized model. And then we're going to look at our expected means. We're going to go down here. And it's going to give us treatment, blue dose, and the treatment by blue dose interaction term. And when we continue with that, notice in our post hoc, you can only do main effects. You can't do interactions. It's the same way with the expected means. It only compares the main effects. Now there's actually a workaround for this that we'll look at in a second. Actually, let's go ahead and do it now. So rather than run this, say OK, we're going to paste. And that's going to create the syntax. So this is what SPSS does behind the scenes. It creates this syntax. And in this case, we have our model asleep by treatment, group, and blue dose. And it comes up and it has the expected means for treatment group, the expected means for blue dose, and it will give us the expected means for treatment by blue dose, but it doesn't give us the statistics. So we're just going to say, well, I want the statistics. So I'm going to write in compare. I want to compare treatment groups. And I want to give for an adjustment an LSD. And then let's run that. And so when we do that, we see, now our variances aren't equal. That's nice. There's no Welch test. Well, I don't remember if we talked about the Welch test. If your variances are not equal in a one way, you can do a Welch test. And that Welch test is, rather than using the general linear model, analyze general linear model univariate, you would go to analyze compare means one way. That's where you get your t-test, but along with the t-test is a one-way analysis of variance. And then in the options or the statistics, you can select a Welch test. And a Welch test will compare if it's if the variances aren't equal. So in this case, we do reject the null hypothesis. We don't for the medians and the others, but this is a test of means, so that's actually somewhat relevant. But there's nothing we can do about it at this point. Now, one thing you can do is we had our interaction is treatment group, high dose, low dose, or low dose. Let's say we have low dose, and then treatment, control, blue blocker, software, high dose, control, blue blocker, software. Now that's a two-way. We make this little two-way matrix of things. But what we could do is just string them on out and have 6 groups. Rather than a 2x3 matrix, we can have a one-way, and then we can run the Welch test on that one way and see if there are any differences that we have to worry about. All right. But let's just, for the moment, assume that the Welch or the variances are okay. And we see here again, we get blue dose is an effective variable. So there's a main effect between high dose and low dose. So that carries over. Still no difference in the treatment, and the treatment by blue dose is not significant. But let's go ahead and copy this into our Excel file. And let's put it down here. That is where we're going to get our error term. And then let's look at our means. What's output over here? And we're going to look at, we're going to come down here to the estimates. Now this is the interaction term. We have our difference here between high and low doses. We have our differences here between our different treatment groups. Down here we have where'd it go? Not quite sure why those post-hocs are down there. We have this. Okay, we have these comparisons. Again, sadly nothing significant, but we have the low dose, the high dose, and then the 6 comparisons within each of those. But here are our estimates. Let's copy them to Excel. And let's put them over here. Yeah. All right, and then I'm just going, I should have labeled these, but I didn't. And then copy that, paste, paste. And we're just going to do a quick and dirty analysis with our graphs. So we're going to highlight, notice I can highlight 2 columns here. And when I go to put in the graph, insert our graph, put it in right here, and it gives me a control with a low high, a blue blocker with a low high, and a software with a low high. And I will have a solid fill. Oops, that's not what I want. Click on a bar and solid fill and transparency so I can see my error bars. Or no, this is, yeah. And then click on these, go to here, make my gap width a little bigger, smaller. Now I'm going to put in my error bars in here. Now, what we see here, this is the low dose. This we can see we have for control with a high dose, the control has a lot less minutes of sleep. With the blue blue blockers, the low dose, they had a fair amount of sleep, but then really knocked down. In the software, it didn't really matter. Remember, that was the flatter curve, the flatter line in the output. There's a little bit better with high dose, but not much. So the software does a little bit better sleeping with the low dose. Well, it actually does worse sleeping with the low dose than the blue blockers. All right. Let's do our error bars. I should have put these guys somewhere else. I'm just making this harder for myself. Let's move these down here. Okay, here's our mean square. Here's our mean square error term. So let's come down here and let's take the square root of our mean square error term. To get our pooled standard deviation. And then let's come over here. Yes, those are the means. Okay, so we're going to do our equals T inverse 0.16 23. No. I'm not sure what the degrees of freedom are here. Let's go back to see if it tells us. Why are you jumping like that? Okay. Let's come up to our notes. All right, it doesn't tell us what they are, so we have to figure out our n. So we're going to go into descriptive statistics and crosstabs, and we're going to do treatment group in the rows and dose in the columns. I'm going to say OK. And so we have 8, 9, 8, 15, 14, 15. Let's copy that over to Excel. Paste it. Oh, this is not good. Okay. We seem to have a bug in the system. So I am going to stop now and reboot and come back. See you in a minute. Okay, let's try that again. I got this to copy in there. And so we have control blue blockers and high and low dose. So we go for n, we're going to have 8, 15, 9, 14, and 8, 15. So our T inverse is going to be equals T inverse 0.16. Degrees of freedom are n minus 1. Okay, oops. I get something here. Yeah, okay, I don't know what happened there, but that's correct. And so now we have adjusted our t's. Now we have to do the same thing. That's the t. Then we have the standard error. And that equals standard deviation. Remember, we need to keep this constant, so we're going to hit F4. So it puts in the dollar signs divided by the square root of n. And we're going to copy this all the way down. And so our 84% CI is equal to T times SE. Copy that all the way down. All right, let's give that a few less decimal points. Now let's add our error bars. So chart, add element, error bars, more options, custom, and then we're going to highlight these guys. Come down here, mean minus those, click there, okay. And now we have our error bars. Those are kind of hard to see, so let's click on the error bar. Let's go to the bucket of paint so that we can look at the line. It's going to be a solid line, and its width, get out of the way, its width is going to increase, maybe that. The one thing you have to be careful with that width is that it also increases the width of the cap, so that sometimes these don't overlap because the cap has gotten too wide and it's actually like 0.045 or something, and it doesn't look like it's overlapping, or maybe it's the other way around. Anyway, they can get confused. All right, so that's how we draw error bars, and that's how we do analysis of covariance. Now, one more thing we need to do, and we should have done it the last time as well, but we can catch up here. We need to look at effect size. Now, and normally when we get significance, we want to see if that significance is clinically relevant. Here we did not get significance, so what we kind of like to know is it not significant because the power just wasn't great enough. And so remember let's look at, let's take control versus low and high. So here we have equals, or no, we're going to do high. Sorry. We want to look at control high versus blue blocker high. So we have equals blue blocker high, because I like the reference to be the second one. So we can, if it's a positive, blue blocker is greater than control. If it's negative, blue blocker is less than control. So the reference ought to be second. So minus that mean divided by the average standard deviation. And what's the average standard deviation? It is the root mean square error term. We hit F4, although I don't think we're going to copy anything. Oops. Problem with the formula. Oh, there's a decimal point in there for some reason. Okay, so look at that. It's a pretty good size. Effect size. Not great, but okay. Let's copy that. And that was comparing blue blocker to control. Actually, let's move this. And at high dose, let's move that, copy it down to here. And what is this looking at? This is looking at blue blocker low, but we want to look at high. And this is comparing software high to blue blocking, dividing by that. So the software to control is only 0.28. So that's how we would compute effect size. And you have to manually compute effect size once you get beyond the t-test. The computer doesn't do it for you. And when it talks about computing effect size, it's talking about the eta squared, not the difference between the means. So in this case, the effect size of, I really don't know why it's doing that. It's very annoying. We come up to main effects. Sake. We'll just come over here, between subjects, tests between subjects, and eta for the treatment group is 890 divided by the total sums of squares, and whatever that number is, that's the eta, that's the effect size, total effect size for treatment groups. All right. That's analysis of covariance. Now let's look at repeated measures. This one, well, I suppose we can stay in the same thing here. Okay, all along we have been treating oh my. All along we have been treating treatment group as though we had 3 separate groups of 23 people each. Now the truth of the matter is, subject 4 here did all 3 treatments. It was a crossover trial. So we've been horrible in violating our assumption of independence. So how can we compare these guys? We don't meet the assumption of independence of observations. So what we're going to do is a repeated measure analysis of variance, where the controls are, where the groups are repeated measures, are repeated. And so all of these are measures that are repeated for each group. Now, as I think about this, we're going to have a problem. We can't do this test with a general linear model with the data in this order. For repeated measures, we'd have to have all these variables for control, and then downstream here in a whole set of columns, we'd have blue blockers and their values, and software and their values. So this would be a much shorter data file, but it'd be 3 times as long, as wide. So we can't do that. So what we're going to do is go to a different database. We're going to go to our Ortho-K, and we see here we have in a wide fashion axial length. It looks wider if we go to data view. So we have AL0, 1, 2, 3, 4, 5. And if spherical and aspherical groups were repeated, we would have a spherical AL to 5 and an aspherical AL0 to AL5. But they're not, they're between. Now what is repeated is I, and the left and right eye. And so what we're going to do is we're going to split our file by I, which we've already done here. Okay, now let's go to the general linear model form of repeated measures. Now the next time we're going to talk about mixed model. It's pretty different from this, but we're going to define a factor. We're going to call it AL, and there are 6 levels, and we're going to add that. So we have this new factor, it's AL, and it has 6 levels. Now we're going to go define it. It's given us a space for 6. We're going to fill it with 6. Let's not include age. All right, now if we had another repeated measures, say our lens type was within, we would have defined 2 variables, and all of these 6 would be axial length, and then there would be another 6 that would be all axial length. And the first half would be spherical, and the second half would be aspherical. And we would name the other variable lens type, and it would have those 2 things. It would break it down into that. So we can still do our means, still compare them with LSD. We can have a between subjects factor, which I think would be nice. Let's put in lens type. And under options, we can test homogeneity of variance. We can do the effect size estimates, but again, that's the eta squared, not the ones we really want. We can put in parameter estimates, make it like a regression. But that's about what we're going to do right there. So, okay. Now I suppose I could have done, well, but let's just look at what it's got. All right, so we have 164 lens type 0 with the left eye, 164 and 100 with the right eye, and so forth. That's our N. And this uses a box test of equality of variance. Oh dear, looks like we are rejecting that. That's because sphere has a lot more variance than aspherical. So technically we should be reluctant to go on. Now, homogeneity of variances, the analysis of variance is pretty robust. The sample sizes are equal. Well, sample sizes aren't super equal here. They are for the axial length. All the axial lengths will have 164 values. But within here, it's not so good. We're going to forget it and just assume that they're equal for now. We have multivariate tests. Now, this, by the way, when we start talking about mixed models next week, is how we get around this problem of not equal variance. We can look at the variance and model the variance as well. In this particular way of doing analysis of variance, you can't do that. All right. So what we have first here is a multivariate test. And we're not going to really pay too much attention to this. This is where your model would be y1, y2, y3, y4, y5, y6 for all the axial lengths equals treatment group plus error. And so a multivariate test, all the axial lengths are on the left side of the equation rather than the right. And it's going to do a test between the three groups, the two groups, the two lens types, and it tests for significance. And it's these that are significant no matter which type of multivariate t-test you do. You could do Eli's, Wilkes, Lambda, Hotelling's, Roy's largest, and they all are significant. Now we run into Montlick's test of sphericity. Sphericity is this notion of the variances, this notion of independence, and the variance being a little different for the covariances. So when we look at AL compared to AL2 and AL correlated with AL3, as the subjects are correlated in their measure, they're close together with each other, but far apart between. And what sphericity kind of has the assumption is that this relationship is constant across all different ones, but it's not independent. There is some correlation. And in that test, you get an epsilon. And the epsilon, it depends kind of, well, for the, so there's the epsilon, and then there is adjustments that you make. There's the Greenhouse Geyser, the Hunt-Felt, and something called a lower bound, which you hardly ever use. That's how bad it can get. You pick between these two. And generally speaking, if this number is less than 0.75, you use the Greenhouse. If it's greater, you use the Hunt-Felt. And where that comes into play is down here. For the left eye, we see we have axial length, and we have sphericity assumed. That's if you don't do any sphericity correction. And then this is Greenhouse, Hunt-Felt, and lower bound. And what is adjusted are the degrees of freedom. And so no matter which one you do, they're significant, but we would report this line that is with Greenhouse because the Montlick sphericity epsilon was less than 0.75. And we have the interaction between axial length and lens type as well. And that also is significant. So both the year, or the axial length by year, the amount of difference for each one depended on which lens type you were. Then we have within subject contrast. Again, we have the left eye and all the stuff duplicated for the right eye. And now we have just looking at the main effect of axial length. This is a linear increase. A quadratic means there's one bump. A cubic means there's 2 bumps. And since we have 6 variables, we can have n minus 1 bump. But really, it gets pretty confusing to interpret, even after the quadratic. The cubic, it just gives it. There can be 2, but it's much easier to just say it's a straight line or it has a bend to it. And if you carried it out, that quadratic would bend and then actually eventually come back down. But usually within the data range, it's a good way of estimating just a little bit of a bend there. And then the interaction says that it looks at this, but for it's a little bit more of an effect for one group than another. And when you plot this out, you can kind of see how it works out. All right. Here's our Levine's test for equality of variance. And it's busting the whole thing out all over the place. Now we're using an unmatched group. In a later video, we're going to do propensity analysis. We're going to match subjects from these two groups, and these problems are going to go away. Here's our test. Now, up in the within subjects, within included axial length, and the within subject axial length by between subject lens type. They're all figured in with the within subjects. They use the mean square error term for both of these. So the F, we're doing Greenhouse-Geyser, so the F is 88.236 divided by 0.382, the mean square error, and that gives us an F of 230. And then the interaction, Greenhouse-Geyser, mean square 26, divided by mean square Greenhouse-Geyser, 0.38, gives us an F of 68.5. Still a pretty big F test. P null hypothesis, not really reasonable with this F size. All right. If we come down here, so Levine's test. Now we look at, is there a main effect? Now there was an interaction, so the main effect here becomes less important. But we can see there is still a main effect of lens type in both left and right eyes. But really it's whenever the interaction is significant, then the group and the group by whatever lens is significant, then there is a significant difference between groups, even if this wasn't significant. All right, notice here we have our estimates, copy, spreadsheet, paste, and here we can, just for the left eye, this is again this is the main effect. Not really what we're interested in because the interaction was significant. But we can get an idea when so each of these years are averaged over lens types. So this is the average of both spherical and aspherical at baseline. Notice, unfortunately, it doesn't carry over the initial thing. So 1 is really axial length 0, and 6 is really axial length 5. So, but in any event, and normally what you do here when you're doing your graph is you don't do a bar graph. but you do a line chart, and we could just do dots, but we're gonna do connect the dots. And so you can see axial length is growing as the years go by, which makes a lot of sense. But let's look at what the what it looks like, what the what the interaction looks like. So we come down here. Oh, here it is. No. I think I didn't ask for it. Let's go analyze general linear models, repeated. It's got it, it remembers it, thank you. EM means. No, I didn't put them in. Okay, let's see what that gives us. If we come down to the bottom, we get this table, copy, Excel, paste. Now again we have the left and the right eye, but now we have sphere. So this time let's do our Excel graph a little different. Let's highlight let's highlight year and the mean, and insert scatter line, and then when we get this picture, this is the spherical. I'm going to right click and select data, and the first series we're going to edit and call it spherical. I just clicked on that so I didn't have to type it. Also, when you do it that way, when you copy the graph, it will retain this label. If I typed in spherical and copied it, that's spelled wrong, I would it would just go to group 1 or something. It wouldn't carry over the name. Now I want to add a curve, and your Excel in a Mac is going to look different from this. So, but you can get the idea of what you're supposed to look for. The series name is going to be a spheric. The X values are going to be these guys. And actually, I could use the same ones as the other one. I'm going to hit this little button right here to save that. I'm going to hit this little button again to do the next one. Copy these down. And here we are. Now, I don't remember which is blue and red. I'd sort of like to know that. So I'm going to come up to Chart Design, Add Chart Element, a Legend. Now where do I want to put it? On the bottom, on the right, the top, the left, the bottom. I see most of them are over here, but that sometimes squishes the graph too much, but not in this case. So a spheric is this group, and spherical is this group. Notice that the spherical lenses grow a whole lot more than the aspheric. Also notice that at the first year, there was a difference between these populations. So this is kind of bad. They're starting off at different places. That's why we're going to do propensity analysis. Match these guys. Everybody will start in the same place. All right. Let's see. If we wanted to add error bars, we could go get our root mean square and put that in there. For this particular graph, since we're looking at the axial length by treatment group, we use the within subject's errors because that's where that test was. If we were just doing a 2-bar plot with the main effect of treatment group, we'd have to use the within subject's errors from the between group. So let's see what I'm talking about here. So for this one, for the graph that we just saw, we would use the error greenhouse 0.382. For the if we were just doing a bar chart for the treatment groups, we would come down here and we would use the error term here. It's a different one, 0.584 versus 0.365. So you can see that's really the between subjects have a lot more variance. You haven't controlled for any when you're looking between. Okay, that will be enough for this videotape. We have looked at general linear model, and we have looked at the least squares analysis programs. These programs all use least squares. We get a mean square error. We can calculate a root mean square error. That's a nice thing, but it requires complete data. We cannot have any missing data anywhere, or we lose the entire subject. The next time we'll look at the mixed model that uses maximum likelihood. It does not have a root mean square, but it does have a variable that's, or a parameter that's comparable, or a set of parameters that are comparable. And we will cover that. So that's it.